Hey guys, nice to see you again. Today I will discuss something about direct mapping in a very detailed manner and the implementation technique of direct mapping, which are basically hardware and software technique. Before we go further, I would recommend you to watch the previous video of computer organization and architecture so that you can get a brief idea about what we are doing right now. And if you know the direct mapping or the mapping techniques, something about it, then you are good to go. So let's get started. Now, what do we have in a direct mapping? So we have one main memory block, and that main memory block, consider this is something value that we are passing in some sort of function, and the output that we are getting is a cache memory block. This is pretty much is the idea of the whole memory mapping thing. Okay, so in a direct mapping, what do we want actually? Let's say we have some blocks of main memory, let's say capital M, and some blocks of cache memory, let's say small m. Okay, and we know that capital M is far more greater than small m. That's the trivial thing. Now, as the output of this function, we want a cache memory block number. So we have small m numbers of cache memory block. If we are numbering that particular block of cache memory from 0, then we might have 0, 1, 2, 3 up to m minus 1 blocks of cache memory. So the answer of this function should be in the range of this 0 to m minus 1. Which function, which mathematical function is um, eligible to give me this kind of answer? So I will go for the modulo operator. Okay, modulo operator is the function that gives me, if I do mod small m with any of the number, the answer will be 0 to m minus 1. Okay, so here in a direct mapping, we are basically using the mod operator or the module operator. But while using the mod operator, uh, there might be one doubt or one question that could pop up in anyone's brain, that what if two memory block would have a same modular result? Okay, that means uh, what happens when two or more main memory blocks that produces the same cache memory block number? Okay, uh, we'll get to this question later, but first of all, let's understand this whole scenario by an example. So we have a main memory of 512 words, cache memory of 64 words, and block size is 16 words, and that gives us the number of blocks in main memory, that would be 32, and number of blocks in cache memory, that would be 4. Okay, so these are the number of blocks in main memory and cache memory. Let's realize, see this one, let's understand this is a cache memory and this one is a main memory. So I would number the blocks from 0, 1, 2, 3, 4, 5, 6, 7, 8 up to, remember this, up to 31. Okay, and the cache memory block will be 0, 1, 2, 3. If you remember, we have discussed 0 to m minus 1, and small m here is apparently number 4. So cache memory block will be 0 to 3 and main memory block will be 0 to 31. So by the modulo operator, by the rule of modulo operator, the number 0 block of main memory will be transferred to, let's say, 0th block of cache memory. Okay, so let me mark it with yellow, and that block will go to cache memory and cache memory number 0. I mean 0 number of cache memory block. And the second block, by the rule of modulo operator, will go to, the first block after 0, the first first number of block comes, and the first number block by the rule of modulo will go to first block. Okay, because it's pretty much clear that uh, 0 modulo 4 is equal to 0, and 1 modulo 4 will be 1. Similarly, 2 modulo 4 will be 2, 3 modulo 4 will be 3, and 4 modulo 4 will be 0 again. 5 modulo 4 will be 1. So we have some of repetition kind of thing here. Okay, fine. So by that rule, the first block will go to first block of cache memory, first block of main memory will go to first block of cache memory, and second block of main memory will go to second block of cache memory. All right, and third block to third block of cache memory. Fine. Now the fourth one will go to the 0th block. So let me color it with yellow. The fourth one will go to 0. Okay, and the fifth one we will color it with blue because it will go to the first one. All right, so similarly, this kind of modulo operation will be performed for all of 0 to 31st different blocks. Okay, and if we move further doing this kind of operation, we will get result something like this. So consider that this one is the cache memory and these are the block numbers. Now these are the main memory block numbers for which result of modulo operation is 0. So all of these blocks will be transferred to the 0th block of cache memory. Okay, and similarly these are the blocks for which the result of modulo operation will be 1, and for them result will be 2, and for them the result of modulo operation will be 3. Okay, so none of block which is in this category, this second category, will be stored in 0th position. This won't happen because the modulo operation of these numbered block will not be 0 at any time, any cost. Okay, so these number of blocks of main memory will be saved if there would be a need to save the blocks in a cache memory, then definitely the block would be one numbered block for this set of main memory blocks. Similarly, for this set of main memory blocks, the block would be zeroth number of main memory blocks. Now, same goes with these two categories. Okay. Now the question arises that there is only the space of one block and we have that several amount of blocks. How do we distinguish that which is the lucky block of main memory, which is obviously saved in cache memory? Okay, so let's see how many blocks are there in each category. In each category we have 1 2 3 4 5 6 7 8. So we have 8 number of blocks in each category, and to distinguish each block I will need 3 binary bits. Okay, so let's understand that these are the individual columns. Okay, consider them that they are individual column like this. Okay. Columns are not straight, but you could imagine them as straight. All right, fine, pretty much in good shape. So let's assign this column number 0 0 0, this column number 0 0 1, this one would be 0 1 0, this one would be 0 1 1 1 0 0, 1 0 1 1 1 0 and 1 1 1. Okay, so 0 to 7 we have assigned each column by the number 0 to 7, so that we can identify that which of the follow the block that belongs to the particular category is stored in cache memory. Okay, so the bit that we have used to distinguish this column are known as tag bits. So if you remember, uh, just now in a previous slide I have written one question in the form of doubt, that what happens when two or more main memory block number produces the same cache memory block number. So the answer of that question is this scenario is the whole explanation of that question, and we use tag bits to distinguish between uh, the blocks that resulted same number of or the same modular result. Okay, understand in this way that these are the blocks 0 4 8 12 16 20 24 and 28. Now these all blocks are in a competition to acquire space in a zeroth number of cache memory block. Okay, they are not in a competition for 1 2 or 3 number of block, they all are competition with zero number. Similarly, block number 1 5 9 13 17 21 and 25 and 29 are in a competition uh, for acquiring the place at one numbered blocks in a cache memory. Okay, so they are basically competing with each other, and the number of blocks that compete for a particular block in cache memory are given by tag bits. Well, now you might be wondering that what are these blocks. Okay, so assume that they are registers that stores that 3 tag bits, okay, for each cache memory block. So let's see this. Assume that these registers contain value 010, 110, 101 and 111. All right. So now we can understand that which number of main memory block is stored in the zeroth number of cache memory block by this tag bit. We know that there are only 8 possible main memory block for that zeroth number of cache memory block. So let's see which one is number of which one matches with uh, 010 number. This is 000, this is 001, this is 010, and bing bing bing, we have winner. So here we will find 8 number of main memory block in a zeroth position at cache memory block. Similarly here we'll find 010, so we have 011 and 100, 101, 110, 111. All right, so 110, that means 25th, 101, that means 22nd, and we have 111, so 31st number of block. Okay, so we have 31st number of block in third number of cache memory block, and that information we have retrieved by tag bits, which are stored in these uh, registers which are associated with cache memory, each cache memory block. All right, so from here I will discuss about the implementation details of direct mapping. Now before I go further, I will recommend you that you should have a proper knowledge about the physical address division in case of direct mapping. Main memory address is divided into 3 parts named word offset, cache block offset, and tag bits in case of direct mapping. Okay, so how would you divide that address bits into these 3 parts? That regarding that I have made another video. You can find the link somewhere on the screen. Yeah, there it is. Okay, so click on that link and see the video, come back here and continue from here. Okay, so let's start with the hardware arrangement of direct mapping. Well, assume that this box is the address of physical memory or main memory. Okay, uh, let's say address of main memory word. Now this is divided into 3 parts. The rightmost part is word offset, the middle one is cache block offset, and the leftmost is tag. Okay, now the square box over here, we don't know what exactly this box is, but this box has some sort of database, what I should say. It is connected with the registers of that stores the tag bits of each and every cache block. Okay, so this block has tag bits saved in the register of given cache blocks. Okay, if you remember, I am talking about this over here. Okay, so these are the registers. Let's say these are the 3-bit registers, and these registers are connected with this block. All right, now as an input I am giving the cache block number or cache block offset, whatever you like to say. As an input I will pass it to this box. I don't know what is the I know the functionality of this box, but I don't know the name of this box. So let's say this is Xbox. Okay, so I will pass cache block number as an input, and I'll get cache block tag of that particular number as an output. So if I am particularly passing certain cache block number, this will give me the output that what is the tag number of that particular block that is currently saved in that cache block. All right, and now the tag bits from the address that we are looking for, from the address of main memory word, will fetch that tag bits and compare with the tag bit that we have got from the Xbox. Okay, and to compare these tag bits, we will use tag comparator. The tag comparator is very easy combinational circuit. You can design the tag comparator. It is basically a bit comparator, that's it, and you can design it with several amount of XOR or XNOR gates. Okay. So it's pretty much easy combinational circuit. Now this tag comparator gives one bit output, either it is 1 or 0. If it is 1, that means hit, and the hit means yes, the word that we are looking for is exactly in the cache memory. And if it is 0, that means no, the word we are looking for is not in the cache memory. This Xbox, let's uh, zoom it in that Xbox. What does that Xbox contains? Let's see. Now this square over here you are looking, consider that this one is a multiplexer. There is another multiplexer behind that, and there is one another behind that. Okay, so uh, the arrangement of multiplexer you can see in a, I have tried to arrange them in a 3D way, so you can see that they are fixed one behind one another. So okay, you can easily see that. Fine. Now these are the multiplexers. All right, so let me draw here. Consider that these are those registers in which the tag bits were stored. Now this is the register of 0th block. Okay, and I have 3 bits of tag, so I will connect in this way. This 0 bit is connected with this. This 0 bit is connected with this, and this 0 bit is connected with this. All right. Then consider that this one is register of first block of cache memory. These both are of cache memory. Okay. So now this one is connected with this one is connected with this second block, and this one is connected with, sorry, second bits, and this one is connected with third bit. Similarly, I have second block, second block stack bit. Okay, and connection looks like this. Okay, and finally third block of cache memory, and the connection is something like this. There's first bit, this one is the second bit, and here third bit over here. Okay, so this is how there's this multiplexers are connected with the registers. Okay, so if you are confused or this design is bit hodgepodge, then let me clear this one. The one I'm showing right now, these connections are actually this one uh, here. Okay, in general, I have said that this tag bits, if you can see the marker over here, these are the connection in detail or in depth I have mentioned here. All right, now, okay, these are the 4x1 multiplexers, 3 multiplexers, and cache block offset. Okay, now which cache block offset is this? This is the cache block offset that in the previous diagram you can see here, the cache block offset that we are taking from the address, okay, as an input of the Xbox. Okay, so this is the input of our Xbox, the cache block offset, and these are cache block offset lines are connected with basically the selection line of all these 3 multiplexer. So all these 3 multiplexers selection lines are combinedly connected with cache block offset bits. All right, so if I'm selecting or I'm searching for the second block, so my cache block offset bits would be 0 1 0. Okay, and that will enable this this and this uh, inputs. So as an output, there will be the result of this register. Okay, so whatsoever is stored in this register will be we can see that here is an output. Okay, so the output is tag bits of given cache block. The tag bits of the given cache block, that means which block is stored in particular uh, in that cache memory block, and the tag bits of that particular blocks will be the output of this Xbox. That means the tag bits of that store that were stored in that register will be the outputs of that Xbox, and that's how the Xbox is constructed with the help of multiplexer. All right, so that was the hardware design. Hardware design is something that once this is established, we cannot make the major change in that thing. Okay, and that's where it is called hardware. Now this is, you can consider that this one is kind of a disadvantage or flaw in hardware design, but there is a benefit. The benefit is that the hardware design gives the best uh, access time of cache memory. Okay, so you will get a really good access time if you are using the hardware, but the flexibility of the system will be compromised. Now another implementation of direct mapping is a software implementation. In software implementation we are using another memory. In this memory, the contents are tag bits. Yes, the tag bits are actually stored in that particular memory. The index of that tag bits or the tag bit words would be the cache block numbers. If you can realize, this is uh, that memory we are talking about. Consider this as a cache directory. Yes, this memory is called cache directory. Okay, the number of words will be equal to the number of words or number of blocks in a cache memory. So in our example we had 4 cache memory block. So the cache directory has 4 words. Now remember, I'm saying words, not block. Okay, so this is 0th word, first, second and third word. Zeroth word is storing tag bits of zeroth block of cache memory. Okay, so I'll mark it as T0. Similarly, the first word in the cache directory stores the value of tag bits of first block of cache memory. I'll mark it as T1, T2 and T3. Okay, so this is something like a memory. Not something like a memory, definitely a memory. Now this will work in this way. Let's see, this is a physical address, and these are those three parts. This is tag, cache block and word offset. Okay, now I will uh, take this cache block and compare with is it 0? No. Is it 1? No. Is it 2? Let's say it's 2. So yes, we'll compare it with we have compared with 2. Yes, the cache block is 2, and then we will compare the tag bit of that address with the tag bit stored in the memory. If it is hit, then yes, we do have that word in our cache memory, and if it is miss, then no, we don't have. Okay, that's how the cache directory works. Okay, okay, now let's see the size of cache directory. So the cache directory has, as I have told, that number of words in the cache directory would be equal to the number of blocks in cache memory, and each word has a size. I mean, size of the each word would be equal to tag bits. So let's say tag bits. This is actually the pure size of cache directory. Okay, so usually the cache directory option is more time consuming compared to hardware design, because the hardware has the delay of first of all the Xbox and then comparator, and these hardware delays are very less compared to the searching time that require in a cache directory. So yes, the cache access time will be more if we are implementing the cache directory method, and cache access time will be lower if we use the hardware design, but again the flexibility would be less. So still we are preferring the cache directory. The reason of cache directory system is still in trend is just because it is more flexible than a hardware design. Okay, because in hardware design we can't do major change, but if we are under the cache directory design, we could we could use the what should I say? Yeah, uh, we could expand our cache memory easily as we want. Okay, so that is the advantage of cache directory design. All right. About the access time. So in hardware mapping, let's see the delay of our Xbox is let's say n nanosecond, and the delay of our tag comparator is uh, m nanosecond. So the total access time would be m plus n nanosecond in case of direct mapping. And if we are using the technique that is cache directory, then obviously the searching time would be the what we say a bottleneck. or the searching time would be the driven factor of access time. That will be in the order of n, where n is the number of cache memory block. Okay, so that would be the order of that access time in case of cache directory.
Thank you guys for watching this video. Hats off to them who watched full of it, and I hope you'll like it. Now, important announcement. My college will start in couple of months. Before that, I want to make video tutorials as many as I can. So if you guys want me to make video on any specific topic of your choice, please write it down in a comment section. And if you have any doubts, query or question, feel free to ask. I'll be glad to help you out. Your suggestions and ideas are always welcome. If you found this video helpful, then I think you won't forget those 3 magical tasks, which are like, share and subscribe. I'll see you in my next video. Till then, goodbye, happy learning.